Hello, in the last videos we discussed many questions of DSU. Let's discuss the next one. You are given a graph connecting of n nodes numbered from 1 to n and n-1 edges. Each edge has a cost C associated with it. You can break any edge disconnecting the pair of nodes in one operation, but you must add the same edge between different pair of nodes. The cost of operation is the cost of edge being disconnected. Return the minimum cost to make graph connected so that we can make any number of operations. For example, this is the given tree initially and we have two different components. We have to make any number of operations, and finally the graph should be connected and we should return the minimum total cost to make that. So from this we can simply remove one from here, this edge, and we can attach between any two nodes of these two groups so that these will become connected. This is already existing node, so just remove this. We have the 5 left, so remove the edge 1 and add this between 1 and 5. And even then we have other component, so take this edge 4 and connect 3 with 5 with edge of 4. So finally what are the edges that we removed and connected again? Those are 1 and 4. So the cost related to this is 1 plus 4, which is 5. So return 5. In this way we have to return the minimum cost to make the whole graph connected. And the constraints are n is up to 1 and 5. So the first idea is simply start with the least edges such that graph becomes connected. So if we observe here more, we simply removed 1 and we removed 4 because those two are the least in individual components. But how many edges we have to remove and how can we find whether finally it is connected or not? So we thought that we can remove the least edge, we can remove from least edge, and from where and how can we know that the graph is connected or not in every operation? So let's take some examples and understand how we can do that. Let's say this is one component, first component, this is second component, and this is third component. So what are the number of edges that we have to remove to make all the graph connected, to make whole graph connected? It is simply the number of components minus edges, because for every two adjacent components we want one edge so that they become connected. So the first edge, these both will be connected, and for this edge the whole graph will be connected. So if we have x components, we want x minus 7 edges to make them connected. So we got the number of edges also which to be removed and added, and also we got how these both conditions. So can we simply start removing from least edges? So let's take another example. So this will fail, for example, like below. For example, this is the first component with weights 1 to 3. This is with 4 and these are also with 4. So we have 3 components. So we have to pick 2 edges so that finally it will become connected. So we assumed that this is also there are 4 different components. So we have to remove 3 edges of least cost. So we will remove this one because this is the least one of all possible. So we will add between these two, and we will remove this 2 and 3 because these two are the least. We will attach this with 2 and we will attach this with 3. If we observe carefully, even then this is not connected because 1, 4, 5 is not connected and this other is a different component. So we were unable to achieve the same thing. We were unable to achieve a single component. Even then we are removing 2 edges. Why is this failing? Because we discussed that for 3 edges, for 3 components, 2 edges are sufficient. But why here is not the case, and why we are unable to make the graph connected even though we are removing 2 least edges? The thing is, we cannot remove the least edges always. We have to remove 2 edges for sure, but we are not sure that we have to remove 2 least ones, because from this we can see that even though we are removing the least ones, the graph is become disconnected because all the edges we are removing are from the same component, so that the original component is being broken, and that's why finally the graph is unable to become a single component. So from this what we can observe more clearly, because it may disconnected again because of the edges we removed. This is what we exactly discussed, but we have to make sure that it is not connected. There is no problem. So from this we are able to understand that independent of seeing the whole edges for the whole graph, what if we deal independently with respect to each component? For example, from this one we noted the least edges which are 1 to 3, and we have removed all these. But the main problem here is the component is the original component from where we are removing edges is being disconnected. So what if we store edges with respect to every single component and then remove the number of nodes minus one number of edges so that it will be connected for sure. For example, we have a single component of size n, we have other component of n2, we have other component of n3 and so on in a single given graph, and let's assume that we are concerned only about this n for first, this component. Then after removing any number of edges, this must be connected, else our operation is being wasted because we are removing all these n edges, and again we have to add another edge also to make this connected. So independent of an extra edge, what if we try to make this complete connected by removing all the least edges from this possible? So let's say this is the component we are dealing with, and n is the number of nodes. So finally, what should be the number of edges in this component so that it will be connected and no extra edge is needed for the next to make this connected? It will be simply n minus 1, which is minimum finite tree. So for n nodes, n minus 1 edges can be short so that the graph is connected. So now what are the edges? What are the number of edges that can be removed from this? It will be simply the total number of edges that are present now minus n minus 1. So that we are able to show that this becomes connected, and the number of edges we are removing, and we will make sure that they will be least, because it is not wrong that we are going to remove the least one. It is correct, but we are not dealing with respect to whole component, with respect to whole graph, and we are dealing with respect to individual components, so that they will not become disconnected. So the number of edges that we can remove from individual component will be the number of edges in that component now minus of size minus 1, which will become minus size plus 1. So this is the maximum number of edges that we can remove with respect to any component. And here we are breaking this one. That's why the graph is being disconnected, because we have 3 nodes. And what is the number of maximum edges we can remove? It will be 3 minus 3 plus 1, which is 1, which is 2. So we can remove which is only 1. 3 minus 3 plus 1, which is 1. So we can only remove 1 edge from this, so that it will, but we are removing 3 edges. So this is wrong. And now how can we continue this? So for every component we have to keep a track of edge weights also, and also we want the component size as well, so that only then we can know how many nodes have to be removed, how many edges have to be removed from every component. So we want the size of component. So simply, how can we do that? We can do that by DSU of 1. So start going through edges and use a map where we are storing the edge weight u2, v and w, and find the number of components, and then we want edges minus size plus 1 edges of least size for all the components individually. Store all these in a vector, and finally we want the components minus 1 number of edges with least cost, because there are x number of components. We want x minus 1 edges with least cost. So we want total the number of edges we are removing are x minus 1. And what are these x minus 1 are? Those should be not least among whole, but they should be least among individual components. So for example, for every component, for example, we already done DSU, right? So after DSU we will get ultimate parent node of every component. So for example, these are all the nodes and these are all the nodes, and the parent of this is 0 and the parent of 1 is 1. The parent of this component is 1, parent of this component is 0. So how can we make sure that indirectly we are removing the least edges from all the components effectively, but not individual component? So let's say we have this one. So for 0, let's assume the edge weights are 2, 3, 4 and 4. So these 4 are the edges that we can remove. And 1, let's assume the number of 1, the edges we can remove are 1, 2, 3. So these both choices we have. And for now, let's assume that we are going to remove, we want 3 edges to connect those. For example, this just means that we have 4 different components individually in the first In the first case, it have 4 components, so I want 3 edges to be connected. So for now, let's assume these 2 are the only components we have, and other 2 components have edges weight very high. Let's assume all are 1 5, so that we are only considering these 2. So we are considering these 2, and we want 3 edge weights. We want 3 edge weights that can be removed. Which are the 3 that can be removed? These are simply these 3, right? These are these 3 because these 3 are the least among the whole ones. For example, let's change these to 119. Then what are the edges that we are going to remove? These 2 from this one and 2 from this one, because these are the least among individual components. So what can we do simply? So for every component, store the number of so for every component we will get what are the edges that can be removed from before formula. So for every component, make a final vector where for every component we will add that number of edges of least weight to that vector, so that we can remove any number of edges from that final vector, but we want the least one, so we will pick components minus 1 number of least edges from that vector, so that we will get the correct answer. Hope you got this. So for every component, add the edges that can be removed, that this number of edges, add this many number of edges of least weight in every component to final vector. So after the final vector, what will it contain? It will contain the edges that we can remove any number of edges from that, because we made sure that we are adding into that only after making sure that the individual component is connected. So after final vector, we can remove any number of edges, but we want the least cost, so we will sort it, and then we will pick components minus 1 number of least edges from that vector, so that we will make sure that it will be finally connected. Hope you got this. Let's check the code. If you have any doubts, comment below, or try to take some trial and understand more. So let's check the code. We are inputting the number of nodes, and we are resizing parent and size, and simply we are storing map of edge weight with respect to weight in a map, and we are merging those both, merging UV. And now we want, so we are going to map, and we are adding the edge weights to component of first one, because id.first represents the node. So we are populating the edges, and then we are traveling through all the components, and then we are finding the number of extra edges that we can remove, and because we want these to be added in the last vector. So we are traversing 0 to extra times, and then we are pushing back xi, because we have already sorted the edges in this component. And then this is indirectly like we are adding the extra least edges from this component to last vector. And then after completion of this, we will sort this again, so that we will get least ones ahead. And then we want ultimate parent nodes of all components, because we are finding the component size. So how can we do that? We can simply store in a set the parents of all the nodes, and then the size of set will be the number of components. So we can simply insert parent of I in the set, and then the number of components will be connection dot size. And then, for example, there can be a case where the number of edges that we can remove are less than components minus 1. In that case, we cannot add the edges. For example, we have 2 individual components, 1 2 and 3 4. 1 2 3 4 are connected, and we cannot remove any edge, right? Because for these 2, this one must be there, and for these 2 also, this one must be there. So we have only one edge and one edge also, so we cannot remove these 2, and we cannot make final answer, because if we remove any edge, that it will become disconnected. So for these cases, we have to return -1. So simply we can check if the number of extra edges we can remove is less than the components -1, then return -1, because we cannot make the operation. And else, we want least component -1 edges. So traverse 0 to component -1, and then add the least weights of last vector, and finally print the answer. In this way, we can find the answer. If you have any doubt, comment below. See you in the next video.